In this final example, in a section on second derivatives, velocity, and acceleration, we are actually going to see how we can apply the first and second derivatives to this particular type of situation. So in reading, we have a model rocket is launched vertically and its height is modeled by h at t equals minus 5t squared plus 30t plus 1. And h is measured in meters while t is measured in seconds. So we have multiple parts to account for, but just to let you know in advance, questions like this can arise where you might be only responsible for solving, say, the final portion of the question or some other intermediate part where particular prompts have not been provided or steps in the process have not been provided. Okay, so let's take a look at part A where we need to figure out the initial position. So in part A, the initial position would be the height of the rocket at time 0, okay, which is the y-intercept of the function h at t. So if you substitute in 0, I think you'll recognize that you're going to get a value of 1. And that 0 went in, of course, into this function here. So we have 1 meter in height. As for the initial velocity, we need v at 0. Okay. Now in this case, the velocity would be the change in the rocket's height over time. So what we're going to look at is the first derivative. Here I'm using position notation with s. We're going to be looking at the derivative of function h at 0. Okay. So what that's going to mean for us is if we can maybe do a couple of things at the same time, let's differentiate that function. So we'd have minus 10t to the power of 2 reduced by 1. So the exponent gets reduced by a value of 1. So the derivative of minus 5t squared would be minus 10t. So I'm just going to put in a 0 for that time. If we take the derivative of 30t, we end up with 30. Okay, and the derivative of the 1 is 0. So in looking at this, we have 30. Okay, units, we're looking at velocity. This is meters per second. Okay, and back in part A, for h at 0, a height of 1 meter. So moving forward, let's look at acceleration. So the acceleration at time 0 is going to be the same as the first derivative, or sorry, the second derivative of that function h at t at 0. So what we're going to do is we're going to evaluate that second derivative where it is 0. Now in the last part, I kind of did two things at once. If you like, depends on your style, your speed, what you could do is very well take some time out to look at the derivatives of the functions expressed in terms of t, and then the second derivative at t, which in this case would simply be minus 10. Okay, so a at 0, we have a negative acceleration of minus 10 meters per second squared. So you can see that the acceleration function h double prime at t is equal to a constant, or minus 10. So what that means is that over the duration of the rocket's flight, we do have a constant acceleration. Okay, in this case it's negative. Negative meaning that it is decelerating. Okay, notice that minus 10 is very close to the gravitational constant of minus 9.8 meters per second squared. So therein we can see that the context and the answer here are fairly valid. Okay, and also take note, despite the fact that we are launching a rocket, we do have to remember that the rocket's acceleration will not be increasing. Okay, its velocity or its change in height over time will be increasing, but due to the effect of gravity on the rocket, its acceleration will be decreasing. Okay, so let's move ahead to part B, and we will look at the motion of the rocket. So we'll determine when the motion of the rocket changes direction. So what we're looking for there is we're looking for where there is a horizontal tangent. Right? Horizontal tangent to the function 2h at t. Okay, so where does that occur? So it makes sense to look for that position because we're dealing with a parabolic trajectory. So do recall that in terms of rocketry, beginning at 1 and blasting off and coming on down, striking the ground here at some particular time, we are looking for a horizontal tangent, which would represent right here our maximum, which occurs at some specific value of t. So let's see if we can't figure that out. Notice that earlier on we did determine the first derivative of the function as minus 10t plus 30. So what we're going to do is we're going to set the slope of our tangent, which is horizontal, to 0. And thus we can solve this simple linear equation for t. So we have t equals 3 seconds. So over here on our graph, at 3 seconds we see the rocket change direction. Okay, it's at that instant when it really doesn't have necessarily a direction. It's neither going up nor down, but it is at the moment where it will change. Its maximum height, well, part C, that's what we're looking for here in part C. So that is to say, what is the y value? Okay, so let's have a look at that and see what we can come up with. So therefore for that, we're really trying to evaluate h prime at 3. Okay, so let's evaluate h prime, or sorry, h at 3, not the derivative function, simply h at 3. So we go back to the original function, substitute in that value, and evaluate. I just want to double check that I do have the right equation written down. Yes, it is plus 30t. So let's evaluate. So that would be minus 45 plus 90 plus 1. Okay, so that looks like 45 plus 1. So 46 meters would be the height at 3 seconds. Part D, let's move on here and see. We're going to determine the velocity of the rocket when t equals 2 and 7. So while I'm going through this, much of this, your intuition will serve you tremendously well, and you should be pausing the video, trying them out on your own, and then coming back and attempting to do more. So t equals 2 and 7. So velocity in this case would be the first derivative. So we want h prime at 2. We would also like h prime at 7. So recall that the derivative function h prime at t was calculated as minus 10t plus 30. Okay, so therefore h prime at 2 would be minus 20 plus 30. which is 10 meters per second. Okay, and then h prime at 7 would be minus 10 times 7, which is minus 70 plus 30, or minus 40 meters per second. So we can see that at 7 seconds, the rocket has changed, definitely is in a falling state, has changed direction from a positive velocity to a negative one. Okay, so the next question we need to ask ourselves is that a valid number for the context? So if the rocket impacts or lands prior to 7 seconds, we know that h prime at 7 does not exist. So let's move forward and see if that's applicable. Not yet, but let's have a look at part E. So in part E, we want the acceleration. So recall that we had evaluated h prime at t, double prime at t, to have been 10 meters per second squared. That is negative 10 meters per second squared. And up here, I believe we did write the units down correctly. Very good. So we had stated in part A that the acceleration would be constant over the duration of the rocket's flight. So we are looking at minus 10 meters per second squared throughout. Okay, so h double prime at 2 is the same as it is at 7, which would be minus 10 meters per second squared. Okay. Part F deals with whether the rocket is speeding up or slowing down at t equals 2 and t equals 7. Okay. Well, there are a couple of things that we do need to take note of, and that is this. When both, I'm going to go with a general notation. So when both velocity and acceleration are greater than 0, or both are less than 0, the object is speeding up. What this implies is that the product of A and V in terms of their sign will always be positive. So that directly relates back to speeding up. And then the opposite is true, that when AV is less than 0, it's slowing down. So that occurs when V is less than 0 and A greater than 0, or when V greater than 0 and A less than 0, right? The object is slowing down. So that implies that the product of A and V will be negative. With this information available to us, we can now go back to this problem and determine if the object was speeding up or slowing down at those two particular times. So I'm just going to reflect back on that portion of the problem, and we are looking at part F, speeding up or slowing down. So if we look at the velocity at t equals 2, let's see if we can spot that. Here we go. So velocity is right here. Okay, so that's our velocity at time equal to 2 seconds. So notice we have positive 10 meters per second. The acceleration, okay, at 2 seconds is here. We've already calculated that value. So that's h double prime at 2 which was the same at h double prime at 7. We have minus 10 meters per second squared. So if we take those two values, okay, so let's analyze the sign of the answer. So for t equals 2 seconds, take note that a at 2 multiplied by the velocity at 2 seconds, so multiplied by velocity at 2 is going to have a negative sign. Okay? So we need to change the orientation of that inequality so it'll be less than 0. Okay, just look back at the values, positive 10 for velocity, minus 10 for the acceleration, and gives you a product that is negative. So for t equals 2, negative value, that implies that the object is slowing down. Okay, and that makes sense, right? As you launch something into the air, as time progresses, when it reaches its maximum, on its way to that maximum, it is slowing down. Okay, for t equals 7, okay, take note that we had determined, if we look back on it, the velocity at 7 was h prime at 7. We had minus 40 meters per second. So that, right, multiplied by your acceleration, right, two negatives under multiplication giving a positive. So we can see that acceleration at 7 and its product with the velocity at 7 is positive. And that implies that the object is speeding up. And one would expect that as an object then returns to the Earth from its maximum, that it should be speeding up over time. So that takes care of part F. And we're down to the last couple, if not one. We want to determine when the rocket will land. Okay, so again, remember you should be pausing through the video, trying things out for yourself, and then going back and attempting it. So we're going to determine the zero of the original function, or zeros of the function. So h at t was given as minus 5t squared plus 30t plus 1. So we do need to set that function equal to 0 to determine when the rocket will land. The unfortunate part is we really don't have tremendously nice values. So we will most likely have to use the quadratic formula to solve this problem. We can quickly look at the value of the discriminant just to be sure of the nature and nature and number of roots. So b squared would be 30 squared minus 4 times a times c. Okay, and we can quickly see that that value will be positive. In fact, it would be 945. So that implies 2 real roots. We'll suspect, obviously, with a y-intercept of 1 for a parabola opening downwards, that one of the roots is negative, the other positive. So let's go ahead and determine those values of t, where h at t is 0, by using our formula. So we'll take the negative of negative of b, which in this case is 30, plus or minus the value of the discriminant divided by 2 times a, which is double negative 5, so minus 10. So what we'll do is let's figure out which one will be negative, and we'll just reject that root right away. So we're going to have, let's simplify things here a little bit, minus 30 over minus 10 would be positive 3, plus root 945 over minus 10, or same thing, 3 minus the root of 945 over 10. So what we can account for in this particular case, oops, right, that should be, one of them should be positive, right? That's better, okay? Have to be careful there. You want to account for the situation where you have, let's just highlight that here, where we have the positive divided by the negative, and that should give us this scenario here where we're actually adding, right? We're adding the negative, okay? The alternative to that is where you're going to have the double negative, whereby you would be adding the result, okay? So just to clarify that. So now let's go back and finish this off. What you can see is that this value over here, this time value, clearly negative, okay, which is in itself inadmissible. Okay, it doesn't make sense in this situation. So what we're going to do is to accept this particular value for t right here, okay? So this would be the time at which it lands. Just to get an estimate on that value so that we have an idea of what the root of 945 looks like. So let's figure that out. 30.7 and change, divide that by 10, 3.0, and then we'll add 3 to that, and we're looking at about 6.07. So to get the exact value in later work, we should use the radical value, but we will record 6.07 in approximation to that, and that's in seconds. So what you can see is that based on the domain that makes sense in this context, 7 seconds, when we go back and we look at areas that concern here, right? For time equal to 7 and its acceleration, when we consider areas where we have that 7, oops, sorry, that's a really bad arrow, where we have that 7 being shown, we know that that's well beyond the domain, okay? So the last part is to determine the impact velocity, which is part H to the problem. So the impact velocity would be the instantaneous rate of change at the landing time, 6.07 seconds. So let's go ahead and figure that out. So the impact velocity would be v at 6.07 seconds, okay? So we're going to approximate, just for the purpose of getting an approximate answer, something that makes sense in general, as opposed to having radicals in our answer. So recall from the work previous to this, the velocity expression was minus 10t plus 30. So upon substitution, and let me get my notations correct here, that's the general form. I'm going to put an approximation symbol in place here to indicate that this is not an exact value, and we should really be trying to incorporate significant figures within our work. So it looks like that at 6.07 we have minus 30.7 meters per second is the impact velocity, okay? As far as significant figures are concerned, with our calculation, really not an aspect of what we're dealing with here. You can see in terms of times and heights, we're looking at one significant figure throughout. And in terms of our answer, we could very well then represent it as such. So to one significant figure, we're looking at, again, this would be equivalent to, say, minus 3, okay, times 10 to the 10 to the 1 meters per second. Okay,